a final example of tying everything together, of being able to use the midpoint rule and the analytic method to be able to approximate volume. We have our function fxy, y e to the x, given the region 0 to 1 on the x and 0 to 1 on the y axis. All right. So remember part A from in the previous was to be able to develop a iterated integral to represent the volume. So that's going to be double integral 0 to 1, 0 to 1, y e to the x, and dx dy, just to make it easy. We're going to use the midpoint rule, and to be able to use the midpoint rule, we're going to start by constructing an xy plane. Now remember, we use m equals n equals 2, so we're going to basically break it up into two rectangles going across, two rectangles going up. Remember, x goes from 0 to 1, so x is 0, x is 1, and in the middle of that, x equals a half, y equals 0, y equals 1 is the span for y, and so in the middle of that, y equals a half as well. We now need to find the midpoints of all four of the different rectangles that we have, and it shouldn't be too difficult. So for this one right here, halfway between 0 and a half is a quarter. Halfway between 0 and a half on the y-axis is a quarter as well. Halfway between a half and 1 is 3/4, or 0.75. And halfway between 0 and a half is a quarter. In our third box, halfway between 0 and a half is a quarter. Halfway between a half and 1 is going to be 3/4. And not surprisingly, the last of these is going to be 3/4, 3/4. All right. Now, the other thing that we have to find is we have to find delta x and delta y. And that's pretty easy. Right here we can see that delta x is going to be a half. And that makes sense because to go from 0 to a half, or from a half to 1, it's always going to be a half no matter what. The change in y is also going to be a half because the change from 1/2 to 0 is going to be a half, and then also the change from 1/2 to 1. So don't always assume that delta x and delta y are 1, or even that they're the same. In these problems so far, I've given you that they will be the same, but that doesn't necessarily mean that they'll always be the same. We're now going to remember that we can find the volume by length times width times height. So the volume of any one of these rectangular solids is LWH, or delta x, delta y, F at xn, yn. All right, so each of the different points. So let's just go ahead and find all four of the volumes. So V1 is going to be equal to delta x, which is a half, times delta y, which is a half, times the function, and remember our function was y e to the x, so that's going to be 1/4 e to the 1/4. And let's just approximate that. Well, it's just going to be 1/16 e to the quarter. All right, so we can just hold on to the exact value, and then at the very end we can just add them together. V2 is going to be a half times a half times y, which is a quarter still, and then the e is going to change to 3/4. Okay, so notice that this was what we used for V1, and this is what we used for V2. And then we can use this for V3 and V4 respectively, so that way we know which of the different coordinate pairs that we're using. Right. So for V3, delta x is a half, delta y is a half. This time the y value is 3/4, and that's going to be e to the 1/4. All right, and I didn't compute before, but that's still going to be 1/16, and that's e to the 3/4 power. The next one's going to be 3/16 e to the 1/4. And then finally for V4, a half times 3/4 times e to the 3/4. And that's going to be 3/16 e to the 3/4. All right. So now the volume, it's going to be equal to V1 plus V2 plus V3 plus V4 is going to be 1/16 e to the 1/4 plus 1/16 e to the 3/4, and then plus 3/16 e to the 1/4 plus 3/16 e to the 3/4. And so the best approximation we can get by using these four subintervals, we have a 1/16 and a 3/16, which is going to be 4/16, which is 1/4 e to the 1/4. And then the same thing here, we have a 1/16 e to the 3/4 and a 3/16, so that's going to be a 1/4 e to the 3/4. If we really wanted to, we could factor out an e to the 1/4 or something like that, but we're just approximating it anyway. So I'm going to shove this into my calculator really quickly. So I have e to the 1/4 plus e to the 3/4, and I wound up with 0.85026 as my approximation. All right, now the best way to determine how good this approximation is just by going through and getting the analytic solution, which is actually going to be pretty easy for us. Right? So remember the original double integral, 0 to 1, 0 to 1, y e to the x, dx dy. That's the same as integral 0 to 1 of y e to the x, so antiderivative of e to the x is e to the x, from 0 to 1 dy. Notice that the 0 does not cancel out the transcendental. So that's going to be equal to integral 0 to 1 of y e to the first minus e to the 0 dy. Or integral 0 to 1 of e minus 1 y dy. Antiderivative of y is going to be y squared over 2 from 0 to 1. We still have that e minus 1. And this time when we substitute 0, it does cancel the bottom out. So this is going to wind up being 1/2 e minus 1. Now let's see what that gives us. So we're going to have e to the first minus 1. And we're going to take half of that, and that gives us 0.85914. All right, so now this is the exact volume. All right, this is a pretty good representation of that. Now we go up here, we had 85026. So if I was to say D, the comparison, the approx was 0.85206. Okay, and again, that's just from right up here. And then the exact, okay, or I'll just say the analytic was 0.85914. So we're pretty close. We're accurate to at least the hundredths place without any sort of rounding. If we wanted to get a percent error, we could, but if we were to just describe this, we could say accurate to the hundredths place. And that's pretty accurate. So in this example, we got a much better representation than the first example, and it's probably because we were over a smaller area. All right, so remember we went from 0 to 2 to 0 to 2 in the last example. This one's 0, 1, 0, 1. All right, so hopefully this gives you a good overview as to what the double integral represents, how to approximate it using the double Riemann sum, and then also how to get the analytic solutions.